Welcome to Chapter 4, the final chapter of the Introduction to Process-Informatics series. Now we put theory into practice with a comprehensive case study, building a soft sensor for a distillation column. We will work through the complete data science pipeline, from exploratory analysis through model deployment. You will learn to handle real industrial data challenges, compare multiple modeling approaches, and deliver quantifiable business value through process optimization. Our case study centers on a real problem facing process engineers daily. A distillation column produces a chemical product whose purity hovers around 96 to 97%. Quality matters. Customers demand consistent purity above 97%. The catch? Purity measurement requires gas chromatography analysis, available only once per day. Our mission: build a soft sensor providing real-time purity estimates using temperature, pressure, and flow measurements. Before modeling, we must understand our data. Time series plots reveal operating patterns, day versus night shifts, weekend slowdowns, and campaign changes. Correlation analysis identifies relationships. Temperature sensors often correlate strongly with each other, indicating multicollinearity we will need to handle. Distribution histograms show variable ranges. Missing value detection is critical. This exploratory data analysis phase often takes longer than modeling, but pays dividends in model quality. Clean data is the foundation of reliable models. For missing values, we apply linear interpolation, filling gaps by drawing straight lines between known points. Outlier detection uses the interquartile range method. Some outliers represent real process upsets worth keeping, others are sensor malfunctions to remove. Normalization scales all variables to comparable ranges. Document every cleaning step for reproducibility. The pipeline transforms raw data into analysis-ready datasets. Raw measurements often miss important relationships. Feature engineering creates derived variables that capture domain knowledge. Temperature gradient, calculated as top minus bottom temperature, represents the driving force for separation. Energy efficiency, reboiler duty divided by feed rate, normalizes energy consumption for varying throughput. Cyclical hour encoding, sine and cosine of the time of day, captures the daily operating rhythm. Good features often matter more than algorithm choice, so invest time in understanding your process physics. We evaluate 7 algorithms spanning simple to complex. Linear regression provides the baseline. Ridge and lasso add regularization. PLS extracts latent variables. On the nonlinear side, random forest captures complex interactions. Gradient boosting iteratively corrects errors. Support vector regression handles nonlinear patterns. Each model is evaluated using time series split cross-validation. Gradient boosting achieves the best performance with R-squared of 0.93. Understanding which variables drive predictions is crucial for process improvement. Feature importance analysis reveals reflux ratio as the dominant factor. Top and middle temperature rank next, and our engineered feature, energy efficiency, also contributes substantially, validating the feature engineering effort. These insights guide operators toward proactive quality management. With a validated model, we can optimize operating conditions. Define the objective. Minimize energy, that is reboiler duty, subject to purity staying at or above 97%. Search over the 2 operating handles, reflux ratio between 2.0 and 3.5, and reboiler duty between 1,300 and 1,700 kilowatts. Search methods include grid search, SciPy optimization, and differential evolution. The optimization reveals that reboiler duty can drop by nearly 9%, while purity rises from 96.5 to 97.1%, clearing the specification. Visualize the solution on response surfaces to verify feasibility. A complete process informatics project follows 8 connected stages: problem definition, data collection, exploratory analysis, preprocessing, feature engineering, model training, model evaluation, and deployment with monitoring. Include iteration loops. When a model underperforms, return to feature engineering. A first process informatics project of this kind typically runs over several weeks. Collaboration between data scientists, process engineers, and operations is essential for success. Congratulations on completing the Introduction to Process-Informatics series. We covered process informatics fundamentals in Chapter 1, data preprocessing in Chapter 2, modeling techniques in Chapter 3, and practical application in Chapter 4. You can now build soft sensors, optimize processes, detect anomalies, and make data-driven decisions. Key Python packages include scikit-learn, pandas, and scipy. Take these skills forward to transform your own manufacturing processes.